morning, Happy New Year. I hope everybody is in perfect health and with a lot of energy to come back to the project. This is actually the first technical session that we have, at least for the doctoral candidates that have enrolled in the project. Actually, the E1 event. Okay. Alberto has allocated a lot of time, but I think we are not going to spend like till 6 in the afternoon. I mean, in less than a couple of hours, I think we should be done. Each doctoral candidate will present a few details or summary of the whole progress of his or her research, and maybe we can discuss a little bit after each doctoral candidate if needed. And well, with no further ado, Alberto will be organizing this session as a chairman. So please, Alberto, go ahead.
Hello. Also, Happy New Year for everybody. And we can start with EC1, Nicolo Antonelli from CIMNE. Please,
Hi.
Nicolo. Yeah.
Yeah.
You can start the presentation as.
Yes. Can you see my screen?
Yes.
Yes. Okay. And yeah, and also the presentation, I guess. Okay. Okay, I'm Nicolo Antonelli, supervisors, Professor Riccardo Rossi and Ruben Zorrilla. Let's start my presentation. I will talk a bit for the one that maybe that don't know what are unfitted methods. Then brief introduction on the shifted boundary method. Then some results on my development of the shifted boundary method in IGA, and finally some comparison between SBM and trimming techniques in IGA. Unfitted methods were born as an alternative to classical body-fitted approaches when we have to represent immersed object or external boundaries. And as we can see from this picture, the embedded boundary is conform with the mesh, with the background mesh. So we have some nodes that represent the embedded boundary, and we can impose the boundary condition along these nodes. This is in general also for FEM, for finite element method. Instead, unfitted methods, the mesh is completely independent from the embedded boundary. For example, we can see in this picture that first we have made the background mesh, and then we have put on top of it the embedded boundary. And then each unfitted methods differs from the other on how they deal and how they take into account the fact that we have to impose some boundary conditions. The shifted boundary method is an embedded method. Is also can be also considered within the family of approximate boundary methods, and has been proposed by Professor Scovazzi, that is collaborating with us, also in trying to use the SBM in IGA. And as we can see, we will consider the blue boundary, that is the best boundary that the mesh can provide to approximate the embedded boundary, the true boundary. Instead, the blue one is called shifted or surrogate boundary. But we will also do, we will also impose some modified Dirichlet boundary condition using a Taylor expansion in order to preserve the same convergence as without the shifted boundary method. And this is the Taylor expansion we consider. For example, consider a finite element problem with a linear basis function. We expect to have a second order convergence, and if we want to preserve the same convergence, we have to consider also the first term of the Taylor expansion, so with the gradient term. And this that you see in the bottom of this slide are the Dirichlet boundary condition that we impose along the surrogate boundary, the shifted boundary. Let's move to SBM in IGA. I have implemented in Kratos, in our software Kratos, within the IGA application, the SBM, so the possibility to impose some SBM Dirichlet boundary conditions. We see here 2 parameter spaces that has inside some embedded boundaries, the green curves. We will consider some surrogate boundary condition, in this case, external surrogate boundaries, and along these boundaries, we will do the Taylor expansion, and we will impose some boundary condition in order to preserve the same convergence. The key point of the shifted boundary method is that when we refine the grid, so in IGA, when we do knot insertion, the surrogate boundary tends to coincide with the true boundary. And Professor Scovazzi proved for FEM all the stability and convergence property are verified. Of course, in IGA, an important feature is to do degree elevation, and we can still do the same with SBM, but of course we have to consider some additional Taylor terms in the Taylor expansion. For example, if we want to use quadratic basis function in IGA, in order to preserve third order convergence, we have also to consider, when we impose the shifted boundary conditions, the second order derivatives, that is in this case that are contained in the Hessian matrix. In this way, we can preserve the same third order convergence. Of course, if we increase the polynomial order of the basis function, we will need additional Taylor terms. We will see soon some results. So just to understand what I mean with external and optimal boundary, we can improve the shifted boundary method. Instead of taking the external boundary, so the red curve we see in these 2 figures, the optimal one, that is the purple one, and in this way we take the best one. But of course, sometimes we are adding some volume, and sometimes we are taking out some volume. So this is still delicate, and we are still investigating. But it is just to show then some results with the external and the optimal surrogate boundary. The results we will see in the next slide are made in Kratos with a 2D Poisson problem, so a simple Poisson problem, using this manufactured solution so that we can compute easily the L2 error of our method. And externally, we consider classical body fitted Dirichlet boundary condition, and internally we will have an embedded boundary, and we consider shifted boundary Dirichlet conditions. The weak formulation we use is, in my opinion, is particularly interesting because it's completely penalty free. So we don't have any penalty term to be calibrated in order to get the solutions, and this is the weak formulation of our Poisson problem that we will solve. This is our first result. We're using the external boundary, so all the cases are in this slide with external boundaries, with P1, P2, and P3, with 3 cases, so the square, the circle, and the diamond. And yeah, so just to explain the graph because it might be confusing. All the red curves are the square, the blue one are all the circle, and the green one are all the diamond curves. We can see that we have some oscillations, but this is correct, especially because we can see that the higher oscillation are for the red cases that are for the square, and with the square sometimes we might be very lucky, and the surrogate boundary might be also it might also coincide with the true one, and sometimes we might be very unlucky. So for this reason we see a pattern in the oscillation. So but instead, for example, for the diamond case, that is the less symmetric, let's say, we see that all the three green curves are pretty stable, but still we have some oscillation because the SBM, because of the nature of the SBM. Let's move on. These results are for optimal boundary. So the best boundary, we can see on the left the optimal boundary for the three cases, still same cases, circle, square, and the diamond. And we see that we get the optimal convergence. So for example, for first order basis function, we get a second order convergence and so on. So with p+1 convergence, but we see, for example, in the middle, this blue peak that we are still investigating, and we will discuss soon what and the reason why we have these strange peaks. But in general, we see that we get the p+1 convergence. Let's see now our graph that compare the body fitted method, the SBM with external, and the SBM with optimal boundary with the same case, that is the diamond case. The brown line are the body fitted. With the body fitted, we mean that we impose the exact boundary condition at the exact location. So we expect that is the best one, of course. Then the optimal and the external, and we can see that the optimal is very close to the body fitted, and instead the external is slightly worse, but is maybe more stable than the optimal surrogate boundary. Finally, we have investigated the condition number of our matrix, because especially for embedded approaches, or especially in a finite element, we have a well-known problem that is the small cut cell problem, that is caused by arbitrary small cut elements that bring very small contribution for some DOF, and so we have almost zero line in our matrix, and so a huge condition number. With SBM, we don't integrate the cut elements as we have seen before, so we don't expect to have the same small cut cell problem. In fact, for example, in this graph, we can see that for P1, P2, we have a normal condition number below 10 to the third power. But already with P3, but also in the next slide with P4, we see that we reach very high condition numbers, and we are still working on this and still investigating why. Actually, if you have any ideas, we would like to hear your ideas. We think now that we have a slightly different problem that I have called it a small active support problem that happen when we increase the degree of the basis function. For example, let's do an example with P4. We know that every basis function has a support that is 25 knot spans, and it might happen that maybe only one of these knot span is active, because all the other that there might be a very unlucky case where all the other 24 knot spans are inside the hole. Okay, the hole we have seen before. So the DOF is active. The DOF corresponding to this basis function is active, but with very small contribution. So we might have a line, the corresponding line in the matrix that is almost zero, and so a very small eigenvalue, and so a very high condition number of the matrix, and these may cause the oscillation we have seen in that strange peak. But we are still investigating this. If you have any idea, please let us know. Finally, I made a comparison between SBM and a timing technique. That is the technique that is already present in Kratos. It's already implemented in Kratos by Ricky, that will be our trainer in the next weeks, and probably he will talk more in details about these methods, this timing technique. And I made the comparison between the timing technique and our SBM. The timing technique basically is, let's say, a CAD-FEM method. We can say that, I think, that using tessellation creates very small triangles along the CAD elements, a CAD knot span, and create a lot of Gauss points in order to integrate well the CAD knot span. Instead, on the right, we see our SBM technique. This is the first comparison we can do for the moment, because it's only with a square, with the example of an embedded square, because with more complex shape, the timing has still some problem that will probably be fixed soon, and I will be able to do more comparison between SBM and timing. But only with the square, we can see that the timing is very good. It's almost the same as the body fitted, but the SBM that is way easier, let's say, than the timing technique is worse, but it's very similar, and of course the convergence is still the optimal one, the P+1. Finally, my future work, my next steps, to optimize my code in Kratos, and maybe put everything in the master of Kratos, so that everybody can use and can, if they are interested, to use and do some comparison with my code in Kratos. In investigating more the problem I have talked few minutes ago, the small active support problem, if it is actually this is the problem, or there is something wrong in my code, maybe, and then start writing a paper about SBM in IGA for simple Poisson problem. Thank you for your attention.
Thank you very much, Nicolo, for your presentation. At the end of the presentation, we have an open discussion. But if you have any question now for Nicolo, you can proceed.
Yeah, Alessandro has a question. Please go on.
Yes, I just wanted to know if we wanted to discuss a bit. I have a couple of questions, if it's possible. Nicolo, great presentation. Thank you very much. I really appreciate it a lot. And you already did a lot of stuff. When did you start, by the way?
Yeah, I started in June, so I had already 6 months.
Okay.
Yeah.
Okay, anyway, really impressive. I have a couple of questions. It's super interesting. It's just an open discussion. I mean, is just to understand better. When you impose a higher order, you impose the higher order boundary conditions with the Taylor series for higher order degrees, how much is the cost, and how much you think this will impact 3D problems, if any?
Maybe Riccardo can answer better, but I try to answer. I think not so much. In Kratos, we can set the degree of the derivatives we need in all the Gauss point for then integrating evaluate all the derivatives of the basis function in the Gauss points. And I didn't do any test in terms of time, but I don't see any difference when I put like 3 or 4 or 5 in the number of derivatives to evaluate.
Okay, I'm thinking in particular when you go towards 3D. Anyways, and the other question, very quickly, is about: have you tried to solve, or you see any problem in solving, or something extra to take care of in solving fourth order PDEs? And then have you also did a comparison between C0 and CP-1 continuity in the framework? I mean, if the same difference, the same advantage for higher continuity in smooth problems is observed also in this framework?
No, we so far we didn't do this kind of test for checking the to checking the continuity. No, and about the problem so far we have just dealing with simple Poisson problems. So yes, so only.
Anyway, there will be plenty of time for discussing in the future. I really appreciated your work. Thank you very much.
Thank you, Alessandro.
I think Ricardo has something to comment.
No, yes, I'm interested in the question, because as long as you have the Dirichlet boundary conditions, I do not see any extra cost, in the sense you only need, let's say you're adding Gauss points on the surrogate boundary, and in there you're computing higher order derivatives, but this doesn't imply increasing any order, or so you have very few. It's on a line, let's say in this case it would be on a surface in 3D. So you have few Gauss points compared to what you have in the volume, and you don't have any Gauss point in the cut elements, let's say.
Yeah, clearly
Yes.
it depends, of course, on the problem. As always, when you do trimming, it depends if it's. There are cases where trimming is super advantageous, where you have a few holes. There are cases where it's not, and in those cases, it may be interesting to see where these places, think of a foam or something like that. But anyway, I didn't want to go deep in the discussion.
You suggest us what you think is worth trying. It would be with. So it is an open question, mine. I don't see. So in the sense, if you have the cut FEM with the trimmed elements, you will have to add quite a lot of Gauss points, quite a lot as all the asterisks you like, okay, in the cut elements, okay?
Mm-hmm.
Even if you do moment fitting, but there is an extra cost. In here, you should add less Gauss points.
Okay.
The situation is slightly different if you want to have a Neumann boundary condition, because in there, you may have to increase support, or you may have, you may convert suboptimally. But okay.
Yeah, this was the third question about Neumann boundary condition, and I decided not to make. But since you are discussing it, good to know.
Well,
anyway,
if you go for, okay, maybe we don't have time, but if you like, we could have a meeting dedicated to this. And
yeah, that would be fantastic, because I'm really a lot interested in this, but not for now. I just wanted to congratulate with Nicolò and to try, since he did a lot of work, to try to, to give a little bit of discussion that is always nice, since there is new scientific work. Anyway, great, Nicolò.
Thank you, Alessandro.
Thank you again.
Okay, thank you. Now is the turn of DC2, Politimi Sisimopoulou. Please, Politimi, you can start with your presentation.
I think so. Yeah. Can you hear me? Yeah.
Yes, now.
All right.
Escaped by mistake, I think.
I'm sorry. I'm back again. All right. Can you see my presentation? And you can hear me, right?
Yes, everything is okay.
Thank you. So I am DC2. My name is Politimi Zisimopoulou. I have started working at CIMNE at the beginning of September. My supervisors are Lucia Gratiela Barbu and Alejandro Cornejo. And my topic is isogeometric discretizations in computational solid mechanics. Since my background is mostly mathematical, we decided that we are going to start with some introduction to structural analysis. And since our implementation is going to be in Kratos multiphysics, also an introduction to C++ was very important. What we also did is to study 1D isotropic damage models, as I'm going to show later. And our next steps are going to be the development of a 2D isotropic damage model.
One thing, Politimi, sorry, can you put it in full screen?
It's
the
not,
PowerPoint?
right?
Doesn't seem to.
Oh, I'm sorry.
But you can share the full screen.
Oh, okay. I'm gonna try again. Now?
Yes. Yes.
All right.
Thank you.
Okay. At the beginning, as I said, we started with the introduction to structural analysis. For that reason, we use Onyate's book, Structural Analysis with the Finite Element Method, Volume 1. We started with a very simple problem at the beginning, 1D truss displacement problem with a distributed load along the truss, but also a point load on the free end. As you can see also on the figure, we use linear FEM basis, but then we moved to NURBS basis of degree P, which was the point that we're gonna work on, like a NURBS basis, where P+1 convergence rate was achieved. Then, as I said, we moved to the C++, studying the programming principles and practice using C++. We delved into topics like object-oriented programming concepts as classes, member variables, methods, public and private entities, class derivation, and so on, and pointers and references. So I could be able to work on Kratos and do the implementations. The 1D isotropic damage model, what we did in that topic is that I created an object-oriented Python code so we can calculate the behavior of a material under the influence of strain. On the graph, you can see illustrated the stress-strain relationship, which is at the beginning linear, and then when the damage was achieved, then we can see the behavior here. This is the load phase, and then we have the unloading phase. And then we loaded the material, and this is what the graph illustrates for this specific variables, Young's modulus, yield stress, and fracture energy. The paper that we studied was Isotropic Damage Models and Smudge Crack Analysis of Concrete by Oliver Xavier. And as I said, we are currently developing a 2D isotropic damage model. And the next topics that we're going to study regarding the structural analysis is the hyperelasticity and the plasticity. That's from my side.
Thank you very much, Politimi. Thank you for your presentation. Does anyone have any question to Politimi's presentation? If not the case, we can proceed with DC3, Andrea Gorgi from CIMNE. Please, Andrea, you can start with your presentation.
Okay, hello everyone. Can you hear me? Can you see the screen?
We can hear you, and now we can see your screen.
Okay, perfect. Okay, I'm Andrea Gorgi, DC3, and my field is the application of IBRA type discretizations to implicit contact mechanics with supervisors Ricardo Rossi and Alejandro Cornejo. Okay, in the figure, there is more or less what I should be able to achieve at the end of the work of these 3 years. Right now, the roadmap that I'm following is started with a study of isotometric analysis and NURBS-based basis functions. I solved a simple 1D truss model and a simple 1D contact model with IGA and an embedded method that is the shifted boundary method that Nicola DC1 previously described. And right now I'm working on the application of this theory to a second dimensional, a two-dimensional model in Kratos. Okay, starting from the one-dimensional example, I try to solve a general case with a simple truss, so with a general distributed load in the bar and general imposed displacements or concentrated loads at the extreme of the bar. Okay, to test my models, I used a manufactured solution. So I started from chosen desired solution with a sinusoidal function and derived in this way the exact distributed load to apply or concentrated load to apply at the extremes. I wanted to test also the potentiality of the shifted boundary method already in the standard IJ scenario without the contact to move in the contact case later with a little more knowledge on the field. So, okay, as Nicola previously described, the idea of the shifted boundary method, that is embedded method, is that we don't have to have a perfectly fitted mesh because we can use a Taylor expansion to shift the boundary conditions to the knot spans that we have. Differently from the case of Nicola, I also try to see what happens in the case of Neumann conditions, of shifted Neumann condition, like the concentrated loads that I have at the extreme of the bar. And the result is that in the case of the Neumann condition, I have to know an additional derivative with respect to the Dirichlet case, and this will lead to a decrease in the optimal order of convergence, because when we have p-order basis functions, we don't know the p+1 derivative. So because it is 0, we don't have enough information to extend the Taylor expansion to such term and obtain the stream approximation error. Okay, these are just some results that I obtained in the case of the simple truss. So this is the standard IGA convergence error that has a convergence rate of p+1 as expected. This is the case of the IGA plus shifted boundary method, but only in the Dirichlet case. So you can see how even if some oscillations are introduced in the convergence, we still have a convergence rate of p+1 because we have enough information on the derivatives to extend the Taylor expansion with to a sufficient order. Whereas in the case of a complete SBM, including also the shifted of dynamic condition, we can only achieve a convergence rate of p because, as I said before, we don't know enough derivatives. The p+1 derivative is 0 in the case of p basis functions. Okay, and then moving to the contact mechanics. This is the general formulation of contact mechanic problems. So we're governing equations for all the bodies involved, and in general, normal contact constraints or frictional contact constraints. In general, in the future, I will also have to include material geometric nonlinearities, heat generation problems, and eventually additional interface conditions like adhesion, lubrication, and so on. In my case right now, I've only focused to the 1D scenario and with normal contact constraints. So the problem is the contact between two trusses with general boundary conditions, as in the case of the trusses of the truss previously described. So Gn is the initial gap, is the gap between the two bars at the beginning of the simulation. And since the normal contact constraints are inequalities and not perfectly equalities, we need particular conditions, particular ways to enforce such constraints. And most famous one, the ones that I implemented right now, are the Lagrange and penalty methods. And basically, the idea is that in the case of a linear elastic problem, like the one that I considered, the governing equations can be imagined as derived from the minimum of the potential energy. And in the case of the contact, we can imagine the potential to have an additional term that includes the contact. And such term has a different formulation for every way of enforce the constraint. So in the case of the Lagrange formulation, we have an additional term in the potential that includes a Lagrange parameter. In this way, we include an additional unknown in the system. So the system becomes larger and more difficult to solve, but the constraints are imposed perfectly, and the Lagrange parameter has the physical meaning of the contact force. And this is a simple case of a point mass with a spring that enters in contact with the soil. And in the case of the penalty formulation, the additional term to the potential is simply a penalization of the gap between the two objects that will enter in contact. Both terms becomes active only in the case of the contact. To study contact mechanics problem, the code has to be able to understand when the contact will happen and when it will not happen with usually a Newton-Raphson algorithm. And in the case of the penalty formulation, the physical interpretation is just to imagine the soil as the very hard spring that allows a small penetration in the system, but just very, very small. And of course, it tends to zero as the penalty parameter increases. Considering the shifted boundary method also in the contact scenario, this is the general discretization. So, okay, above we have the standard IGA with perfect fit, and below the case of an unfitted method with the extreme that are not perfectly interpolated. Okay, the idea is always to use a Taylor expansion to extend the knowledge to the surrogated extreme that we had with the unfitted formulation. Okay, as in the previous case, I considered manufactured solutions. So I started from a desired solution for the displacement of the first body, of the second body, and a given contact force. Okay, this is the final solution that I used for my case. Okay, this is just a convergence plot of the case of the standard IGA. And here I show the comparison between the standard IGA case with the perfect fit that preserves the convergence rate to p+1. Here there is the case of IGA plus the shifted boundary method with the Lagrange method for the inverse constraint. Okay. Here the convergence error is bounded to velocity p, because we have to shift the Neumann conditions that are imposed to both the trusses in the system, and you can see how some oscillations enters in the system due to the lucky or unlucky cases of the discretizations. And the last graph is about the IGA plus shifted boundary method with the penalty constraint method. And you can see how the convergence rate is always near to P, even if when we are close to low error, some strange oscillations appears. This is due to the fact that the penalty coefficient introduced some air conditioning in the system, and of course, to achieve very low convergence, very low errors, we have to impose a very high penalty parameter. The higher it is such parameter, the more the oscillations appears. Okay, next steps should be, as I said, to understand the available contact mechanic application in Kratos in order to create an IGA model, at least in two-dimensional, with plane stress or very simple scenario for the moment, and after extend the analysis with the shifted boundary method. Okay, thank you.
Okay, thank you very much, Andrea, for your nice presentation. If anyone have any question, or if you prefer to ask in the open discussion. Okay, so we can move on to DC4, Juan Ignacio Camarotti from TAPS. So Juan Ignacio, you are ready. You can proceed with your presentation.
Okay, I proceed with my presentation. Thank you. So, are you watching my full screen?
No, it's not full screen. We are seeing the PowerPoint.
Okay. Now?
Now, yes, I think so. Thank you.
Okay. So first of all, good afternoon to everyone. So my name is Juan Ignacio Camarotti. I'm from TU Braunschweig in Germany. My position is DC4. So I'm a doctoral candidate in the field of co-simulation strategies involving IBRA for the solution of multi-field problems. My work is currently being supervised by Professor Wuchner here in Germany. And my start day was November the 6th, so 2 months ago. So the main objectives of my research are developing mapping operators between different discretizations, the combination of different solvers by suitable coupling algorithms and effective data transfer, and the assessment of IBRA solver benefits in surface coupled problems, for example, fluid structure interaction problems. Okay, so my background is related to aerospace engineer, so I would say I have quite a strong and good background in fluid dynamics and structural mechanics. But at university for my master degree, I have not worked with NERV's geometrical modeling and EDA. So basically, the main focus during this period of time was first to establish a robust foundation on isogeometric analysis, IBRA, and coupled problems. And the main objective during this time was to familiarize myself with the Kratos multiphysics framework and to gain a brief understanding of co-simulation strategies. So basically, the steps during this time was first to introduce myself to NERV's geometrical modeling, then revise basically the foundation of isogeometric analysis and isogeometric boundary representation analysis, IBRA. then introduce myself to a couple problems, but with a particular focus on fluid structure interaction simulations. And as well, a brief introduction to Kratos multiphysics. Okay, so as I mentioned you, the first topic I tried to cover during this period of time was basically NURBS geometrical modeling. So for this particular topic, the main references which I went through were, first of all, the NURBS book by Pigel and Taylor, which is, let's say, one of the best books from my point of view when it comes to NURBS. And secondly, the isogeometric analysis toward integration of CAD and finite element analysis by Cottrell and Hughes, which is as well the foundational book in EGA. So related to NURBS, I began my journey into NURBS by revising Bezier curves and surfaces, where basically I learned the concept of control points and how these control points govern the form of your surface or of your solid. Then the next phase of my learning process was going to B-spline curves, surfaces, and solids, where I basically learned the concept of knot vector, and I immersed myself in the Cotes-de-Bourg recursion formula for the computation basically of the B-spline basis functions. And my focus was as well on the main mathematical properties of B-splines. So basically, when I started reading about B-splines, I realized the big mathematical advantages in comparison to the classical piecewise polynomials using finite element, which I would say that the most important one is the higher inter-element continuity between the elements in EGA. So with a strong foundation in B-spline curves and surfaces, I moved to the representation of curves, surface, and solids using non-uniform rational B-splines, which are basically a generalization of B-splines. And I also revised TRIM's NURBS surfaces for the representation of complex forms, free shape forms. Okay. So basically, my first conclusion when I studied NURBS is that they are the standard model description within CAD system because of their smooth and accurate representations in 3D modeling. You know that NURBS allow for the exact representation of conic sections and other complex shapes. So that's why they are the preferred model for CAD systems. They offer superior flexibility and control over the shape of curves and surfaces. Also, it's important that they fulfill the necessary conditions in order to be basis functions, basically the partition of unity and linear independence between basis functions. As well, they enables a seamless integration between geometric design and analysis processes. That's basically the foundation of EGA analysis. And as I commented before, they have excellent mathematical properties, especially their higher internal element continuity. Obviously, it's infinite between two nodes, and CP minus K at the boundary between two elements, where P is the degree of the basic functions, and K is the multiplicity of the nodes you are considering. And another important aspect is that they have local support. Okay. Of course, they have as well some drawbacks. The first one is that they do not necessarily interpolate the control points. Its computation could be computationally expensive, particularly when you are dealing with high degrees or a large number of control points when it comes to complex surfaces like airplanes or ship hulls. Then another important disadvantage of NURBS is that they don't allow pure local refinement in the NURBS patch. That's another important disadvantage. Another important disadvantage appears when you start considering trimming surfaces, because they introduce discontinuities in the basis functions you are considering. Okay, so that's all regarding the disadvantages. So then after starting the mathematical foundations of EGA, I started learning about isochrometric analysis, with my main focus being on the main differences between EGA and classical finite element analysis, which was the one I have expertise with at university. So for this topic, I used the same book from Cottrell and Hughes, which is the foundational book in EGA. And my learning path started first with the elements definition in EGA, then with the nodes and degrees of freedom definition in EGA. Then I studied mesh refinement strategies, basically odal elevation, knot insertion, and K refinement, which is basically a combination of the two before. And then I studied some elemental numerical integration techniques for EGA. Bueno, so the peculiarities of EGA with respect to classical finite element analysis are basically, first of all, that they use the same basis function to represent both the geometry and the solution field, thus bridging the gap between the CAD and CA model. There is no need for mesh generation, and there is no geometrical error thus. Then another important difference is that the control points used for generating the geometry are the one which carries the degrees of freedom, but they are not necessarily placed on the NURBS curve. So that's something important to have in mind. Then in EGA, an element is defined by a non-zero knot span. And another important point regarding numerical integration techniques is that in EGA, you need an additional mapping from the parameter space to the Gaussian space where you are executing the integration. So that's another important difference in comparison with classical finite element analysis. And another important difference is that in EGA, the Dirichlet boundaries condition inside the patch must be weakly enforced. Okay, after studying the classical isochrometric analysis, I jumped to an introduction, a very brief introduction to IBRA, which is basically a generalization of EGA. And for these purposes, I read it and studied two different papers. The first one is called Analysis in Computer-Aided Design, Nonlinear Isochrometric BREP Analysis of Shell Structures by Breitenberger and Apostolatos. And the second one is called Realization of CAD Integrated Shell Simulation based on IBRA, where they basically, in this paper, they treat all the data structures used for the numerical realization of IBRA. So these two are the two main references used for studying this particular topic. So the learning path was first learning what's the boundary representation of the model, which is basically composed of its geometry and its topology, faces, edges, and vertices. Then I learned the concept of isochrometric boundary representation elements, which basically are used for enforcing different types of boundary conditions, namely, Dirichlet, Neumann, and coupling between different patches in the case of multi-patch problems. And then I went to the techniques used for the numerical integration of trim elements, basically the nested Jacobian approach and the IBRA workflow. Okay, so which are the main points related to IBRA? The first important point you have to consider is that the classical isochrometric analysis works effectively until the point you start considering trimming operations. So that's basically how IBRA appeared. So in order to be able to work with trim domains, So IBRA can be considered as a generalization of EGA that basically uses the boundary representation of the design model. In addition to the same basis function you use as well for EGA in order to approximate the solution field. And as I told you, IBRA provided a novel approach to address trimming. Basically, the idea is to keep using all control points included in the model, so in the untrimmed patch, but with the slight difference that when you are numerically integrating the patch, you just consider those control points which are on the gray surface, let's say, inside the patch. That's the main idea. And the VREP edge elements, as I told you, are used for patch coupling or the imposition of Neumann or Dirichlet boundary conditions in a weak sense, basically using penalty approaches, Lagrange multiplier methods, or niche methods. Okay, so as I told you, my PhD project is strongly related to coupled problems. So that's why, talking with my PhD supervisor, we arrived to the decision that maybe starting with a brief introduction in coupled problems could be a good idea. So I took the decision of starting a joint course between the Technische Universität München, the TU Braunschweig, and the CIMNE related to fluid structural interaction problems with open source software, basically with Kratos. So I'm currently doing this FSI course. And the main contents which were covered in this course first was an introduction to multiphysics, especially to coupled problems and coupling strategies, which basically in the case of two-way coupling are monolithic or partition approaches. Then we studied the balance equation for the incompressible fluids and their discretization with FEM. In my case at university, I work with CFD problems, but using the finite volume method. So this discretization with FEM was completely novel for me. Then we went to the problems related to the Galerkin finite element formulation for the Navier-Stokes. Basically, the problems arising in convection-dominated problems, and the one related to the velocity pressure interpolation pairs you are using. We also revised some stabilization techniques for these problems. Then we studied the AL formulation for mesh movement and deformation. And during this week, I'm currently at the Technical University Munich, because we are carrying out some projects related to fluid structural interaction in using the Kratos framework. So this is basically my first contact with Kratos multiphysics. It's a good starting point. Okay, so as I told you, the last point I revised during this time was a brief introduction to Kratos multiphysics, for which my main references were, first of all, the foundational paper by Dat Band and Professor Rossi, where they presented this framework called Kratos. And then I also attended a course at the TU Braunschweig related to Kratos multiphysics. So during this time, my learning path was first learning the general structure of Kratos, basically with its kernel application. Then to learn how the object-oriented paradigm was applied inside Kratos with its main, which were basically the main classes related to FEM in Kratos. Then I learned the Kratos data structures. Okay, some of an introduction about GitHub and how you develop Kratos with all the master branch and all that. Then I ran some test cases using the Python interface. Okay, so basically the Kratos main feature is that it's a framework for parallel multiphysics problem development, which is coded in C++ and has a Python interface for basically for running your simulations. It's open source and free. And it has a modular structure with the kernel and with many other applications like fluid mechanics applications, structural mechanics, meshing, co-simulation, etc. Okay, so for my next step, what I plan to do is, first of all, to delve into co-simulation strategies, beginning with a literature review and a subsequent analysis of the co-simulation application within Kratos multiphysics. Then I plan to acquire some hand-on experience and proficiency in Kratos multiphysics, which I'm starting during this week in the FSI course. Then I'm planning to develop a deeper comprehension of the EGA application within Kratos multiphysics. Then to broaden my understanding of the mapping operators and the mapping application in Kratos. and then to implement some benchmark problems for co-simulation within Kratos multiphysics and evaluate the performance of the various co-simulation strategies. Okay, that's all for my presentation. Thank you very much for listening.
Thank you very much, Juan Ignacio. Any question for Juan Ignacio? Okay, thank you. Time to DC5, Maram Al-Kafai from TAPS. So, Maram, if you want to proceed.
Hello. Hi,
Hello.
can you hear me? Everything is okay.
Yes, and
Perfect. I'll share my screen. Is it on full screen mode?
No.
the case.
I'll try again.
Yeah, share the full screen better, and then.
Okay, so now it's perfect. Okay.
Yes.
Hello, everybody. This is DC5. My name is Maram. I will take this opportunity to also introduce myself since some of the supervisors are not aware. Sorry, not aware. They don't know me yet. Perfect. So we start. My name is Maram. I come from Jordan. I'm 25 years old. I have recently joined the program. My academic background started with a bachelor's degree from Jordan that I finished in the beginning of 2021. Afterwards, I went directly to the master's. I finished in the September of 2023. My master's was in an Erasmus joint master degree program focused in advanced solid mechanics, where this is a program that is offered by more than one university. I had the specialization in mechanics of structures. I managed to study in 4 different universities, starting with the University of Lille in France. Then I moved to University of Calabria in Italy, and then National Technical University of Athens in Greece. And finally, I did my thesis in Wrocław University of Science and Technology in Poland. During my time in University of Calabria, I had the opportunity to know more about IGA. Therefore, I decided to go with the position DC5 that is focusing on large deformation for the structural elements using IBRA. That is offered by the University of Braunschweig in Germany. The start date was in December 2023. So the most wonderful time of the year. So the objectives for my position are to develop the structural elements in a large deformation setting using the isogeometric boundary representation analysis, where we are going to address the challenges that will come up along the patch boundaries and the trimming curves. And of course, this will be applied using the Kratos multiphysics that will enable a direct CAD integrated simulations. So far, since I started in December, the early progress have been focused on forming that foundational phase, where I'm focusing more on having that theoretical understanding that will prepare me for the practical applications and the modeling part. So far, the educational trajectory started with getting the introduction to NURBS, then in-depth study of the IGA fundamentals, and afterwards I have started exploring the IBRA concepts, and along with that I have been trying to focus on exploring the IGA in thin wall structures. So far, let's start with the NURBS introduction. My key reference was the NURBS book, was and still. The NURBS, we all know that they offer a geometric fidelity, and because they have the local shape control, and they are perfect in most CAD systems. Sorry. Afterwards, I have been working, I have studied in the IGA fundamentals, because we know that IGA gives us the unified framework, and it has more leverage than the normal FEA. Refinement in this part of this, in this method, doesn't read remeshing, and it gives us higher order continuities. The reference has been the isometric analysis by Hughes. Then I have been exploring the IBRA concepts with the most famous paper, the analysis in computer-aided design, the nonlinear as a isogeometric BREP analysis, where it has been like it gave me the introduction for the B representation element and the IBRA itself. And of course, the penalty formulation and basically enforcing coupling in direct boundary conditions. And so far what I'm in right now is the research in the thin wall structure with the work of Kendall, where I'm focusing to see how this can be implemented on shells and beams and the optimizations techniques. As for the upcoming focus for the position I'm in, that means I'm going to also stay more dive into the context of IGA in the thin wall structures, and also to know more of IBRA in that sense. Gain proficiency also in Kratos software, which means that I would need to also gain knowledge more in C++ and Python. And then we're gonna apply the theoretical of that what we have learned in IGA and IBRA in Kratos. And then there's going to be simulation, especially in large setting deformation. And that's it. Thank you.
Okay, thank you very much, Maram, and welcome to the project, because it's the first time we meet you. Okay, if anyone has any question, please just interrupt me. This is time for DC6, Lucas Venta from Universitat of Pavia.
Hello, everyone. Let me share my screen. Okay. I hope you can see it, otherwise stop me. Okay, so, well, I guess so. So basically I'm DC6 and my project goes on mathematical tools for immersed IGA, and it's supervised by Alessandro Reali, Carlota Gianelli, and Giancarlo Sangalli. So, an outline of this rather brief presentation. I will give a brief overview of my project, then kind of state the things I've been learning about in the literature review, and then talk briefly about the next steps of my project. So within this framework of finding or further developing mathematical tools for immersed IGA, we want to study accurate and efficient integration tools, multi-patch coupling strategies, mesh adaptivity, focusing on local refinement and other features always within the framework of IGA. In this slide, I'm specifically showing the work of a colleague of mine with his collaborators, where they basically worked on an adaptive scheme, an adaptive IGA scheme for an additive manufacturing process, where they basically propose a scheme to follow the local nature of or the localized nature of the problem, where we have basically a heat source moving longitudinally across a plate, no? And well, here I'm basically I found these two images that I found nice to explain some of the things we would want to achieve or continue working on. Regarding the literature review, I have essentially a finite element background, so I've been working on introducing myself to IGA. Prior to the introduction of this method of IGA, we always, as some of my colleagues mentioned, we had different descriptions of the geometry represented in the CAD models. So the introduction of this new method allows to provide an end-to-end methodology that unifies the geometrical design from the CAD and the analysis of the PDEs, and hence the solution that we are searching for with the several different problems that we are studying. It's actually here I found two workflows that I found quite useful for myself to understand this difference. And essentially on the left, we represent the workflow from the FEM analysis, where we see that we consistently need to generate an approximate geometry and discretize it. And this has been proven to take most of the analysis time when studying these kind of problems. No. Also, it's important to remark that every time we use the refinement, we need to refer to the exact geometry. Hence, we need to get back to this NURBS representation of our geometry, which comes from the CAD file. No, this is, however, circumvented in the isogeometric analysis. Following this line of the NURBS and to understand the foundations of IGA, I started by studying the basics of the Bernstein-Bezier curves to later extend them to the theory of B-splines in the context of IGA. With that, I studied some of the properties that were already mentioned by some of my colleagues, and well, the affine transformations that come with the change of the positions of the control points, and then as the final step to understand NURBS as a tool for representing very complex geometries and conic sections. I also studied some of the refinement strategies that are used in IGA, and also how they differ and in what they differ with respect to the finite element method, which is what I'm more familiar with, or what I used in the past. And then also the ways or the tools to build domains with multiple patches, which is also included thoroughly in the literature. The next steps for my research come still with some literature review that we need to get our hands on, mainly regarding local refinement, where we will work with hierarchical splines and hopefully yes, and then with phase field models in the context of IGA. Although I'm familiar with phase field models, I have some experience from my master's thesis. This time it will be a bit different since we're under the umbrella of IGA. This will be also combined with studying several different code frameworks to implement these problems. I've already started working with NewTubes, which is a Python-based framework, and it's widely used in our group here at the University of Pavia. But there are other frameworks such as GeoPDEs or Kratos, to which we will get thoroughly introduced in the course in Barcelona at the end of this month. So I'm looking forward to that, and yeah, thank you for your attention. I will stop sharing my screen.
Thank you very much, Lucas. Now it's time for DC7, Ángelos Pagonas from University of Pavia.
Hello, just give me a second. Okay. Sorry, I have to give some permissions because it's Google Meet instead of Zoom, but okay. Is it working?
It's working, but it's not full screen.
Okay. Okay. Hello, everybody. I'm Angelos, DC7 from University of Pavia. I have a very short presentation since most of my time the previous months was dedicated to studying. So I started with a revision of the finite elements method. In general, my background was mainly more user-oriented and applied. So the last time I remember coding and dealing with, let's say, all this backend stuff of finite elements was years ago. So for the purposes of my PhD topic, I needed to look again and more in detail this time in the theory of FEM from a more academic and fundamental point of view, and especially to understand better the mathematical concepts of FEM. Most of this revision process was made through the book of Fish and Belitsko and the first chapters of Tom Hughes' book on FEM, and also through the lectures of Professor Strang in the course of Computational Science and Engineering 1 in MIT. A topic that I had no previous experience is the geometric modeling of curves and surfaces. So I studied some parts from the Farin's book, and it helped me establish an understanding of the topic. The book starts from simple concepts and algorithms and builds up to more complicated cases like rational B-splines and tensor product patches. A nice addition for introduction to B-splines is the last part of this course from Politecnica of Madrid about curves in engineering and architecture. The visual representations and of the mathematical concepts that were also described in the book really helped me a lot. For sure, I need to study more on this topic in the future, but it was essential to have a basis in order to understand better the concept of IGA. And for an introduction to IGA, I am studying the book of isogeometric analysis, and alongside watching any lectures or video material I can find online. Not everything is yet clear to me from the first 4 chapters of the book, but every time I revisit the information, my notion of the isogeometric analysis is improving. And recently I started exploring the Nautilus framework in order to have a more hands-on learning experience. I haven't achieved any results to demonstrate, to be honest. I mostly play with the existing examples and try to understand how the code works. This is an example of an infinite plate with a circular hole. And some of the next steps. So I would like to emphasize more on hands-on learning through Nautilus. Also try to modify the existing examples and understand the underlying structure, and also revisit the IGA book to develop more confidence in topics that are not yet clear. So that's all from me. Thank you.
Thank you very much, Angelos, for your presentation. And finally, it's time to DC9, Philip Lee from Q Leuven.
Hello, just 1 second. Can you see my screen? No.
Yeah.
You can see it, right?
Yeah.
Okay. So hello, I'm DC9 from KU Leuven in Belgium. And first of all, a short recap about my research topic. So what I'm going to do in this project is I'm going to do model order reduction of coupled vibro-acoustic systems. So this involves in where we discretize this structure by using finite elements, and the acoustic domain is discretized by boundary elements, and we want to combine it with the IGA framework and use model order reduction for the combination of IGA in combination with FEM and boundary elements. Also, we want to extend it in the future with fast assembly methods like fast multipole or H matrices in this framework. So in order to make my life easy, I considered only one domain for now, so the acoustic domain. So in here I have listed out an overview of what I did in the first 2 months. So first of all, I want to give you guys a short motivation and also fundamentals of acoustics, and then walk you guys through the other points. So in acoustics, we want to solve the Helmholtz equation, which is highlighted here in blue. And with this, by solving this Helmholtz equation, we can solve it for interior or exterior problems. So in acoustics, the quantity of interest is the sound pressure. So in the literature, there are 2 methods we got in order to solve this equation, which are the direct and indirect boundary element method. And in this project, we've chosen to use the indirect method, because with the indirect boundary element method, we can solve combined interior and exterior problems with open boundaries, which is not possible with direct BEM. So because we use IGA, that means that usually you approximate the single and double layer potentials with Lagrange polynomials. In the sense of IGA, we use NURBS and control points in order to do that. Right, so a little recap from the introduction from the last presentation, why we do it. So we choose boundary elements methods to tackle acoustic problems, because we only need to discretize the boundary. So we only have to discretize a surface instead of a volume in finite element method. And furthermore, by using the boundary element method, the Sommerfeld radiation condition is also automatically fulfilled, which is not the case in finite element methods. And because we deal with numerical methods, they are very sensitive to the geometric description of the surface. That's why we wanted to include IGA in order to diminish the geometrical error. Well, it seems that the boundary element is very superior to the finite elements, because, as I mentioned before, we deal with less degrees of freedom. But the main drawback of boundary element method is that the matrices are dense, non-affine, and also highly oscillatory, so complex. That's why we want to incorporate model order reduction in order to reduce the overall computational time. Right, so moving on to the IGA implementation. So I implemented an indirect boundary element method with IGA for our 3D sphere, and applied it only for this example for now, because the sphere is actually a quite beautiful example, because it has an analytical solution to it. So I can compare my numerical results with the analytical one in order to verify my code. So in this case, my 3D sphere has 6 non-conforming patches, and I computed the double layer potential for it, which you can see in figure 3b. But the results seem a little bit wrong, because patch coupling is not included yet. So next step was for me to include the patch coupling, and I used here methods from one of our former colleagues, which uses virtual refinement. So in figure 4, the concept is actually displayed. So in the top left corner, you have two patches which are non-conforming. So that means that they have not the same number of interface variables, and the method basically wants to virtually refine the interface degrees of freedom to make the number of the interface degrees of freedom equal from patch 1 to patch 2. And after that, you can then use a substitution method in order to enforce continuity. So I've done that and displayed here the double layer potential with the enforcement for 100 Hertz. This is the top view of it, and displayed also the error from 0 to 100 Hertz. Right. Good. So next step, I did then model order reduction. So as I mentioned before, the boundary element method deals with full matrices, so which are non-affine and highly oscillatory. That means that if we do a frequency sweep, we have to assemble the system matrix every single time, and the computational cost increases with the increase of the frequency range that we want to analyze. So that's why model order reduction comes into place. So what model order reduction does is it finds a low order model that approximates the full order model and gives good enough results, and is also computational cost efficient. So figure 6 should depict schematically what it does. So we have a reduced model in which the dimension is much smaller than our full order model. Right. So there's actually a big problem in which we cannot directly apply model order reduction with BEM. It's actually the non-affinity that I mentioned. So what I mean with non-affinity here is that the frequency dependency, so the angular frequency, cannot be extracted from these system matrix. So every entry of the system matrix is involved in the angular frequency. So it's so even by finding a reduction basis, we cannot reduce the computational cost, because for each frequency the matrix has to be assembled. And the idea is hereby to approximate the boundary element system by an affine expression. This can be either used with Taylor series expansion, or here with Chebyshev polynomial approximation. So for those of you who don't know Chebyshev polynomials, so Chebyshev polynomials are polynomials that are related to the cosinus function, and I've plotted it here for the first kind. And so the system matrix can then be represented by a sum in which C1 SCI represents the Chebyshev polynomial, and TI and QI are the parameters which are independent from the frequency. So we only have to solve the system at certain frequencies, which are here the Chebyshev nodes. So the Chebyshev nodes are the 0 points of our Chebyshev polynomials. Right, by approximating it with an affine expression, this does not solve our problem because we still have to assemble and store all these parameters. So what we can do is we can apply a Gajokan projection in which we approximate the exact solution by reduction basis V, times our X tilde here. And the projection basis can hereby be obtained by a so-called Krylov subspace. So what it does is we so because we are dealing with systems that change in frequency very slowly, we can use subspace recycling. And so what we do is we expand our Krylov subspace for every frequency and generate our basis by orthogonalizing the Krylov subspace and construct our basis. So now we have our basis V, and we can reduce the dimension of it. So I've depicted it here schematically just to make it very clear. So in here we have our full model, order model in which Ti is the dimension of mxm and is also complex, and Qi is just a vector with dimension m. So in our reduced order model in which we computed our basis, we can multiply our system matrix and reduce it into a much smaller dimension, which is then way faster to compute. So I've done it here for the sphere again. So I've selected the number of Krylov vectors in the subspace, which is 150, and only sample through 4 frequencies, and computed my reduction basis and compared it to the analytical solution in here. So the main drawback of this method is that for creating the reduction basis, the number of Krylov vectors and also the number of sampling frequencies in which we would sample is predetermined by the user, and normally this is normally you don't know this beforehand, so you don't know how many sampling frequencies or how many Krylov vectors you need. So the motivation is hereby to find the optimal settings, so the number of order of subspace dimension, and also how many frequencies we sample. So my co-supervisor developed hereby an adaptive procedure which does that. So in each dimension, so the subspace dimension and also the frequencies are determined iteratively and are compared then to the results are then compared to user threshold, which is predetermined by us. So I did that here. With figure 8, I just wanted to show that with the automatic Krylov subspace recycling, you need way less sampling frequencies, and also the number of vectors that are needed is also less than for the fixed Krylov subspace recycling. It should just show you that with the automatic Krylov subspace recycling, the method is superior than the fixed one. Figure 8b should then represent the absolute error between the double layer potential between the full order model and also the used algorithm. Yes, so yeah, so what I did right now is just consider the acoustic domain and implemented yeah, some model order reduction schemes to it. Because IGA screams for shape optimization, I want to incorporate, yeah, multi-parameter model order reduction. So yeah, consider multiple parameters into it, especially the control points, which are used for shape optimization. And I also want to extend my work by incorporating the structure. So I want to couple, yeah, use coupling just at the interface. So where both domains are separated. Right, and also use small order reduction schemes to it. That's basically it. Thank you.
Okay, thank you very much, Philip. And thank you very much to all the fellows for your nice and interesting presentations. So there is room for an open discussion. So if any of you wants to discuss something specifically, so it's time for that.
I was curious about the refinement. I don't remember who was describing it, but it was from Pavia. I don't remember the name. Apologies. But you were describing that you want to, I think it was Lucas.
Yes.
You want to do refinement in the context of figure. Can you put the 2 words about how would that work?
Okay, let me. So basically, this was. Should I share my screen? So, or which you mean like which to which examples it would be applied, or?
No. How the technology works. So how are you defining locally? This is, I understand that that's a paper, but if you could just say it in 2 words.
So basically, what I saw from that paper, which is in collaboration with Carlota and Alessandro and their students, is that they use like truncated hierarchical splines, and then they use like an algorithm for the refinement to basically, yeah, adapt it to the. But maybe they can say like some more.
If you want, I may add something, Lucas.
I would love if you may.
So to reply to Riccardo, essentially there are different possibilities within the spline context to do adaptive constructions. And one of these is the one that Lucas mentioned, and more or less it relies on a hierarchical approach where different levels of refinement are encapsulated in some kind of spline hierarchy. Otherwise, one could also define splines on T meshes or locally refined B splines. So there are, I would say now, quite a rich literature on these different techniques. There are pro and co to choose one of them. And for some of them, there is also an adaptivity theory within the isogeometric context. So I don't know, this was just a quick reply, obviously. We can say much more about this.
Could you just point us to, let's say, one article to read? I mean, if you have to pick one, tell us, read this, and so we can take a look. I understand that the literature may be wide, but...
are you more interested in the spline construction or in the adaptive methods for IGA?
In the adaptive methods for IGA, I would say, but...
Okay, maybe the most comprehensive paper is, I can send you the link if you want, is some kind of review on the mathematical foundation of adaptive isogeometric methods, and includes more or less quite a rich bibliography where you can then find different construction.
Okay, if you may, that would be at least, okay, I admit my ignorance on this, so we can catch up.
Yes, if I can add a few things, the point is this, that I suggest maybe Carlotta can send Alberto such that he can share with everyone a couple of papers, maybe this one that she was mentioning, and maybe also one or two on the construction, because of course, you know, you need to do the activity, but you need to build the spaces. So just to have a look at that, if you don't use codes where these things are already implemented, then there are tools available. And this is the main reason why we asked Carlotta to join the project, is exactly because of this technology, truncated hierarchical splines. She is the first author of the first paper. So this is, she's the real expert in that. So we can really discuss about that also for inclusion in Kratos in case and so on. But probably the best thing is if Carlotta gets a couple of basic papers and maybe a list of other references to be put in the shared folder of all the DCs.
Yeah. So if you may, it would be really welcome. Also because for the SBM and specifically for the case of the Neumann condition, we were considering to increase locally the order. Andrea was looking into it, and he had some success and some lack of success, let's say. Maybe Andrea, you may comment on that. But I don't know if for contact we will go into SBM or we will do CAD-FEM. That's still to be decided. But at least that's the possibility of increasing the order locally would be appealing to us, or to adapt, either refine or increase the order. So we would be really interested. And also that would apply very well to the case of the fluid, of course. So, okay, nothing. Andrea, do you want to comment anything about, because you worked a bit on this, so if you want to make any comment.
Yes, I tried to look if there was a possibility to increase locally the order of the nerve space functions, and I found some papers about the changeable degrees nerves. It's like I could share some papers, but when I tried them, even in 1D, I mean, my idea was to see if increasing locally the order of the basis function near the Neumann boundary, I could achieve some knowledge about the derivative that I needed for the extension, for the shifting of the Neumann condition. And okay, in the end, I had a benefit, but not in terms of increasement of the convergence order. I don't know if you remember when I showed the presentation before, but with Neumann condition, basically I reduced the order of 1 in the convergence in IGA. And if I increase the order locally, as I said, with these changeable degree space functions, basically I have a factor of benefit that increases with the order of the basis function, in the sense that the higher it is the basis function, the higher it is an increment, but it's not one order more. It's not the optimal convergence, still not the optimal convergence.
It depends also if you are just increasing the order, or you would aim also to increase the continuity. No,
I increased also the continuity. I mean, with normal basis functions, the continuity should be p minus 1. If I connect 1 not span with basis functions of order p to the not span where I increase the order, and I can increase the continuity to p instead of p minus 1, but the convergence doesn't change so much. I mean, I just have the factor of benefit. If you want, I have the graphs of the result that I obtained. But
Yes, I don't know.
I
Now,
don't
what
know
I
if
want
there
to
is enough
mention is
time.
that obviously one has to pay attention, and there is also a strong difference if you're trying to do this in 1D or in 2D. For example, these local refinement possibilities I was mentioning, some of them also allows P refinement and also K refinement, let's say. So increase the degree, so or the order, what you want to use, and or the continuity. Some others may only increase the degree, but keeping the same regularity, or just doing H refinement instead of P refinement. And another observation is that in the IGA context, the H refinement capabilities were probably not so much exploited in connection with the P refinement, also because of the difficulties in this setting.
So, I mean, just to make a comment a bit. Okay, here we have 3 theses, okay, here at CIMNE. One is on fluids, and in fluids, it would be more than fine to me to have H refinement. The point is, this is the thesis of Nicolas. Andrea will be working on contact. So in contact, the point is that our error will be governed in this case by what happens at the interface. So we wanted to consider using the SBM and to refine locally. Of course, we are aware that in 2D or 3D, it will be more complicated, okay? Way more complicated. But to do so, we need to do it not in a Cartesian way, let's say. So I don't know if I explained myself. Yes, I think as Lucas was showing. So we need to do something like Oct3 to understand. I understand that Oct3 is, I mean, just refining the 2 directions or in the 3 directions. But our hope was that we could increase the order locally and by that recover the global order of convergence. So go back, so having I'm going to say a polynomial of order P everywhere and P plus 1 just close to the boundary in the hope of recover P plus 1 convergence. I don't know if I explain myself or... So the point is that if you wanted to use SBM and recover P plus 1, then you have to extrapolate the gradient. Let's say to extrapolate the gradient, you need 1 order more, essentially. And essentially, that's not a trivial thing to do. We have no obligation of going for SBM. This is true. We had the hope we could go that way because it has some nice features. In particular, you don't have to generate the integration over the cut elements, okay? But again, we have no obligation.
Yes, okay. We have no obligation of doing anything. I mean, we have obligation to do good science. So it's interesting, and I think we should really discuss deeper this, Riccardo. Maybe later on we can have a meeting also discussing this topic that is surely interesting. I understood perfectly what you want to do. And I think it's doable.
Okay, so that's all on my side. Thank you. We will read the papers and get back to you.
Yeah, and on the other side, I will definitely study more the shifted boundary to be ready for a discussion. I read a couple of papers already, but I want to go a little bit deeper in that direction. Anyway, we'll have time for discussion for sure. Worst case scenario, we'll meet all together in Florence, so there will be definitely time for that.
Okay. So all on my side.
Okay. Alessandra and Carlota, if you share with me these papers and references, I can upload it to the Google Drive share folder. Okay.
Alberto, maybe
yes.
We can discuss the topic that I brought up in my email.
Yeah, sure. Yeah.
So first of all, thank you all for the updates. It looks impressive for so few months of the project running. So I wanted to bring up a bit the topic of the ISMA conference, which is going to take place in September. So I had a talk with our conference manager, and he let me know that it is possible to organize a dedicated session for ISMA, for GECKO within ISMA. But we need to have at least 4 contributions, and they need somehow to be related with dynamics or NVH applications or something like that. As I said to my email, from our side, we can have at least 1 contribution, but I wanted to discuss with you all if you think it's possible to have at least 3 more contributions from within the consortium.
That's going to be September 2014, right?
September 2024, yes.
Sorry, 2024, of course. Yes. 2014, I'm from that you see that I'm old. 2024, okay. Because of course, dynamics is among the topics that we are very much interested in studying, but when you need an answer.
Yeah, let's say as soon as possible, maybe in the next couple of weeks, just to know if we can count on this special session or not.
Dionysos,
yes.
Would it be fine if we do something with CFD in that context or no? There is the dynamics in the computational fluid. So,
I think it's structural dynamics, that conference maybe.
That's why I'm asking.
Structural dynamics and NVH, but I think if we have a couple of contributions from CFD, it wouldn't really harm, as long as we have also core structural dynamics and or NVH applications. So maybe we can see some of these methods and one application on structural dynamics or NVH problem.
So one other question is exactly when are the dates of the conference?
Let me check to be accurate.
From 9 to 11, according to the website.
Exactly, yeah, 9 to 11th of September.
Okay.
And we were planning to link, I think, the public technical course organized by Braunschweig and organize it locally in Leuven.
And the point is that there, of course, because the point is you need to be sure to have at least 4 contributions to be able to run a session. Then because to be fully speaking, without any filter, even if I don't know if you want to speak really without any filter, since we are recording and then putting this freely online, right? No,
but this is off topic, so we can cut the video before.
Okay, yes. Just to know.
We can edit it.
No, because the point is that if the conference organizers ask you to guarantee 4 talks to have a session, we at this point, and you commit to that, and this point we don't know if we have 4 talks from students, maybe we can say that with some other research that we are doing, we say, okay, maybe 4 topics we can cover, 4 talks we can cover, including maybe presentations from also the advisors. Then, if at that time we have enough material for students, that's the way to go. But maybe, an advisor can be a backup with some other research, just not to fail if at the end of the day, one talk is short. we are short one talk. I don't know. I'm just putting their ideas.
No,
because
for
now
sure.
it's a little bit from our side in Pavia. Now it's definitely too early to guarantee a topic from one of the two DCs.
I completely understand, and that's what I said in the email communication previously to Alberto and Alejandro and Ricardo, that it's either the DCs or the scientists in charge. So it's not a problem if the advisors come in and replace the students. It's just that we need to have 4 presentations to have a complete session, let's say.
Because in principle, just I'm speaking for Pavia, we will have, I don't know if for September, probably not, but maybe later on for sure we'll have some results in dynamics. This is among our interest. We have working on dynamics as well, and so both in space-time, IGA, or in standard, time-stepping methods. I have to check the dates. Me and Giancarlo, we have to check the dates to be sure that in case we can replace. And then instead, if there is some advancement from the disease in that direction, of course, that's the first choice. I don't know. But I need to think a little bit more about that and checking the dates and checking a bit the website of the conference.
Let's say the following. From Barcelona, we can send someone. We are willing to send someone. I think it will be mostly related to Nicolas' work because he's the one that is more related to dynamics. Okay, but we could do something basing on, let's say, Helmholtz equation or something like that. So if there is the common decision to organize something, then we will submit something. Alessandro, if from your chair you can, or any of your, from Florence too, if you can, and there is a third, I understand, Dionysos, that you can send someone.
Yes, for sure.
If there is someone else, Roland, for example, could you eventually send someone to ISMA?
Well, I cannot say right now, but I need a few days to try to organize, and I will give you a reply later on. I don't know about Roland.
Yeah, so I need to think about that as well, but I think we could have someone.
I don't know if you hear him, but he's saying that he needs to check, but probably yes. Okay, so let's.
It's not guaranteed that one of the new DCs.
No, it's not an issue.
We can do something.
So that's what Alessandro was telling. So let's say, let's give us, let's say, 1 week, Dionysos, and
for sure.
Ping us so that we need to reply to you by the end of next week, let's say.
That's more than fine. That's more than fine. So I just wanted to bring this up so that everybody can have a thought about it, and if there is somebody that is fit for this conference, and if we have enough people, then we can organize a special session. Otherwise, we can leave it for the moment and maybe organize it in 2 years from now.
I think that if you could organize a session, it would make sense. So
yes,
also is a way to meet and to team up.
Yeah.
Okay. So anyway, let's fix an internal deadline by the end of the next week. Nicola, on our side, please, you keep it in mind because you are the candidate for this. Okay.
Okay.
I am an expert in brown dispatching, as you see.
Okay.
In Italian, we say scaricabarile. Okay.
Yes, scaricabarile. That's a better translation. Sounds better, actually.
Okay, thank you. Any other thing to discuss or? Okay, so thank you to you all very much for this amazing first technical workshop of the project. And the next steps of the project is we will see all Philips in our next training week in Barcelona. Is the next time we will see each other. So we are delighted to receive you here in Barcelona. So thank you very much, and see you all here in a few weeks. Thank you.